the chemical shield that makes this bug taste like poison to predators. Not a metaphor, not an exaggeration, an actual engineered molecular weapon built into the body of an insect you've probably flicked off your windowsill without a second thought. Somewhere, right now, a bird is learning a lesson it will never forget, and it's happening in someone's backyard, in real time, without a single person noticing. Meet the stink bug, specifically Haliomorpha halis, the brown marmorated stink bug, a species that looks almost comically unthreatening. Shield-shaped body, mottled brown coloring, slow and clumsy in flight. If you had to guess which backyard insect was carrying a functioning chemical defense system, this would not be your first pick. And that's exactly the point. Here's what's actually happening beneath that unremarkable exterior. Tucked into the thorax of every stink bug are specialized structures called metathoracic scent glands. Think of them as tiny, biologically engineered chemical reactors, sitting quietly, doing nothing, until the moment something threatens this insect's life. The second a predator makes contact, grabs it, or even just gets too close, those glands activate, releasing a fast-evaporating liquid through a rough patch of exoskeleton called the evaporatorium, a structure specifically shaped to disperse the chemical as fast and as widely as possible. The engineering behind that structure is worth pausing on. A smooth surface would let the liquid pool and drip away slowly, wasting precious seconds the insect doesn't have. The evaporatorium's rough, textured surface does the opposite, maximizing surface area so the compound turns to vapor almost instantly, flooding the immediate air with concentrated deterrent the moment it's needed most. It's not an accident of anatomy, it's a dedicated piece of biological hardware, shaped by evolution for exactly one job, and it does that job in a fraction of a second. And what's actually inside that liquid is where this stops being a simple defense mechanism and starts becoming something closer to genuine chemistry warfare. The two dominant compounds are called trans-2-octanol and trans-2-decenol, long-chain aldehydes that are, on a molecular level, close relatives of formaldehyde. These aren't just smelly. They're reactive, irritating compounds capable of causing real physical reactions on contact, from skin staining to respiratory irritation, even in something as large as a human being. Now imagine what that same chemical does to a bird or lizard that just tried to swallow one whole. The taste alone is enough to end most predator encounters permanently. Animals that bite down on a stink bug describe, or rather demonstrate, an immediate and violent rejection response. One bad experience, and most predators learn instantly, never to try again. This isn't subtle deterrence. It's a hard, unforgettable lesson delivered in a single bite, and it works so well that in parts of the world where this species has spread, adult stink bugs have essentially no natural predators willing to risk it a second time. And here's a strange twist that makes this whole story even more surreal. Those exact same compounds, trans-2-octanol and trans-2-decenol, are actually used, in isolation and in tiny controlled amounts, as flavoring and fragrance additives in the food industry. Separated out and diluted, these are the same molecules that give certain foods a faint fruity or green aroma. Combined together, at the concentration a stink bug produces, they become an instant, universal predator repellent. Same chemistry, completely different outcome, purely a matter of concentration and combination. But here's the part that turns this from clever defense into something genuinely unsettling, once you understand the full picture. Scientists studying these same aldehydes discovered they're not just unpleasant. In laboratory testing, trans-2-octanol and trans-2-decenol showed measurable antibacterial activity against some of the most dangerous pathogens known to modern medicine, including MRSA, E. coli, and Pseudomonas aeruginosa. This tiny, unassuming insect isn't just producing a bad smell. It's manufacturing a compound with genuine antimicrobial properties, sophisticated enough that researchers are now studying it for potential medical applications. In one study, researchers went a step further. They coated ordinary mealworm beetles in these same stink bug compounds and exposed them to bacteria that would normally cause serious infection. The coated beetles showed dramatically reduced bacterial colonization compared to untreated ones. In other words, this chemical doesn't just repel threats after the fact. Applied directly, it can actively prevent an infection from taking hold in the first place. The same way a surgeon might apply an antiseptic before an infection even has the chance to start. Let that sink in for a second. A backyard pest most people consider nothing more than an annoyance is quietly producing a molecule that can fend off predators, ward off fungal infection, and inhibit some of the most stubborn, drug-resistant bacteria on the planet, all from the same tiny gland. Most defense mechanisms in nature do one job. This one is doing at least 3, simultaneously, with zero conscious effort from the insect itself. Here's a question worth sitting with while we're in the thick of this. If you had to design a defense system from scratch, would you build something specialized and devastating for one specific threat? Or something like this, less flashy, but effective against nearly everything at once? Because evolution clearly bet on the second option here, and it's hard to argue with the results. Let me know which strategy you'd have picked. There's a reason this particular defense evolved to be this broad, and it comes down to survival math. A single insect can't fight off a bird, a fungal infection, and a bacterial threat with 3 different specialized tools. There isn't room, energetically or biologically, to build and maintain that many separate systems. So evolution did something far more efficient. It built one weapon capable of solving multiple problems at once. A single chemical cocktail, flexible enough to repel a predator's jaws and a pathogen cell wall. That efficiency is part of why this species has become such a successful invader outside its native range. Heliomorpha hales originated in East Asia, but has since spread aggressively across North America and parts of Europe. And in these new environments, local predators simply haven't evolved the instinct to avoid it. The chemical shield that took millions of years to perfect back home becomes an almost unfair advantage somewhere entirely new. A defense mechanism nothing in the local ecosystem knows how to counter yet. In some regions, that advantage has translated into staggering population numbers. Without natural predators willing to learn the hard way, and without the ecological checks that exist in its native range, the brown marmorated stink bug has become one of the most persistent agricultural pests in the country, capable of damaging entire crops of fruit and vegetables, largely because nothing local has yet figured out how to stop it. That's the strange, double-edged nature of a defense mechanism this effective. What kept this species alive for millions of years in Asia has, in a new environment, turned it into something closer to an unstoppable force. And it's not just predators this chemical is meant for. The same alarm compounds double as a warning signal to other stink bugs nearby. Release that scent, and you're not just defending yourself, you're broadcasting danger to every other member of your species within range, essentially shouting a chemical alarm that says exactly what just happened and where. One insect's bad encounter becomes instant, actionable intelligence for the entire local population. It's a form of communication that doesn't require sound, sight, or proximity in the way we usually think about warning signals. No calls, no visual displays, nothing that a predator could learn to anticipate or intercept. Just an invisible chemical cloud, drifting on the wind, quietly telling an entire population of insects exactly where danger is, without the threat ever knowing a message was sent at all. It's worth pointing out what this defense system isn't, too. Despite the reputation, despite the smell, despite the almost cartoonish level of chemical warfare packed into something the size of a fingernail, stink bugs don't bite, don't sting, and don't transmit disease to humans. This entire elaborate molecular shield exists purely as a last resort, a deterrent triggered only when the insect believes its life is genuinely in danger. It's not an aggressor. It's a creature that spent millions of years building the ultimate leave me alone button, and rarely, if ever, needs to actually use it offensively. Compare that to almost any other heavily defended creature in nature, and the restraint here starts to look genuinely strange. Venomous snakes still hunt actively. Wasps still sting proactively when their nest feels crowded. But a stink bug's entire chemical arsenal sits completely dormant, unused, for the insect's entire life, unless something specifically tries to kill it. It's less a weapon and more an insurance policy, paid for once through evolution and almost never actually claimed. Which, in a strange way, might be the most impressive part of the whole story. This isn't a predator hunting anything down. It's not chasing, stalking, or attacking. It's a slow, clumsy, unremarkable little insect that simply refuses to be an easy meal, and has the molecular engineering to back that refusal up completely. No venom, no speed, just a chemistry set evolved over millions of years, sitting quietly in its thorax, waiting. If insects quietly hiding genuinely unhinged biology under the most boring possible exterior is your thing, make sure you're subscribed to Six Legs Deep, because that's basically the entire premise of this channel, and we've barely scratched the surface. If a creature this small and this unassuming can carry a defense system flexible enough to repel predators, fungi, and antibiotic-resistant bacteria all at once, using nothing but 2 simple molecules, what else is crawling through your backyard right now that you've never once thought to look at twice? Somewhere out there, on a leaf, on a windowsill, on a wall you walked past this morning, that same quiet chemistry is sitting ready, waiting for a threat that might never even come.